Hi, good morning, ladies and gentlemen. Gonna go through a quick video here for today's topics. Um, as you may have noticed, after looking at the Ed puzzle and reading the section yesterday, we have started a new chapter. The new chapter is chapter 8, and it is entitled Work, Power, and Simple Machines. So today we're going to go through the first bit of that, which is a discussion of what work and power are in physics. Um, if you go into Schoology, and my view will look a little different from yours, of course, because I have the teacher view. But in order to find the materials for today's lesson, you're going to click on second marking period. You're going to select week 7, December 7th through 11th, and then of course today's date is Tuesday the 8th. In that folder, you're going to find several files. One of them is a PowerPoint, which we're going to be looking at here shortly, and if you want, you can go back and review it on your own. And the other is a work and power calculations PDF. Okay, that PDF there, you're going to need to upload to Notability. We're going to be doing some writing on, and we're actually going to use it again tomorrow to solve some problems. And eventually it'll end up being submitted, not today, but eventually. So anyhow, get that work and powers calculation PDF set up in Notability maybe before we start. Okay, I'm going to go into now the PowerPoint and talk a little bit about what work and power are um, in physics. Okay, so again, the chapter is entitled Work, Power, and Machines. When we hear the word work used in common usage, it's often a term that is a synonym for effort. Okay, if you put out some sort of effort, you are doing work. Maybe even doing your homework, for instance, is considered work if I'm doing schoolwork. Now, in physics, that term has a totally different meaning. Okay, so we're going to try to focus on the physics definition of work as opposed to the way work is used in everyday society. Um, what is work? Okay, well, in physics, work is when a force is applied to an object and the object moves in the direction of the force. Okay, it is calculated with the formula. Work is force, which is measured in newtons, multiplied times the distance, measured in meters. Okay, and the formula is down the bottom of the slide there. Work equals force times distance. So here you can see a couple of instances, little pictures, and maybe you can think a little bit about whether or not what is taking place in those pictures qualifies as work according to the physics definition of the term. Okay, so I want you to think about a couple different situations based on what we just said, and you can think about whether or not you think work is being done or not. So, would mowing the lawn be considered work? How about weightlifting? How about if you pick up a piece of furniture and carry it up the stairs? How about if you push against a locked door? Is that considered work? And then finally, swinging a golf club. All right, well, let's go through mowing the lawn first. So, of course, mowing the lawn, a person applies a force to the lawnmower, and the lawnmower moves in the direction that that force is being applied. Okay. Now, weightlifting, I don't know why this was the example for weightlifting. Of course, this woman is lifting a package of groceries. Okay, but if she were to grab a package of groceries and pick it up, is that considered work? There's a person moving furniture up the stairs, and there's the swinging of the golf club. Okay, so let's go back to mowing the lawn. If that person is pushing on the lawnmower and the lawnmower moves in the direction that that force is being applied, then yes, that is considered work. How about weightlifting? If I pick a barbell up off the floor, or say I'm doing bench press and I'm pushing on the weights in an upward direction away from my chest, and the weights move in that direction, is that considered work? The answer is, once again, yes. Okay, if I move furniture up a flight of stairs, I'm applying a force to the furniture in the direction, then yes. Okay, how about the next one? Pushing against a locked door. So if I push against a locked door as hard as I can and I start to sweat and my muscles start to ache because I am putting in effort, a lot of people would say that I am doing work, right? Again, this is where we get confused because we tend to think of work as being a synonym for effort. But in this case, because the door is not moving in the direction of the force, this is not considered work, right? Pushing against the locked door is not work. Okay, and then finally, swinging a golf club. Okay, so if I exert a force on the club in the direction that the club swings and it moves a certain distance, that one also is considered work. So yes on that. Okay, so just some different instances. Okay, does work have anything to do with speed? So if I do a particular job, if I mow the lawn in half the time or twice as long, does the amount of work that I do change in those two instances? And the answer is no. Work does not have anything to do with time. It is only force and distance. So if you mow the lawn in 2 hours or you mow the lawn in 1 hour, you still did the same amount of work. Okay? Of course, no work is done when you stand in place holding an object. So here's a question for you. I have a set of stairs, maybe in your house, maybe at school, whatever you want to imagine. Is it more work if I walk up the stairs slowly or if I skip up the stairs, 2 stairs at a time as fast as I can to get to the top? And the answer to that question is the work is the same. Oh, I'm sorry, I accidentally skipped to the next slide here, but the work would be the same in the last example. It doesn't matter how much time it takes to get to the top of the stairs. Anyhow, I accidentally skipped on, so we're going to keep going from there. The unit, which we have not introduced yet, used to measure work is called a joule. And it is the equivalent of a newton of force exerted over a meter of distance. Okay, it's named after a British physicist, James Prescott Joule, and there's a picture of James Prescott there. Okay, but just remember that the unit of work is the joule. All right, moving right along. Now we're at the concept of power. So again, this is a concept that you may have heard before. You use the term power. What does power mean in physics? Well, power is the measurement of how quickly work is done. Going back to the lawn and mowing it in 1 hour or 2 hours, this is not a matter of work, it's a matter of power. Okay, power is the amount of work done per unit of time. Okay, if 2 people mow 2 lawns of equal size and one does the job in half the time, who did more work? Well, we just answered that question. They both did the same amount of work. But the person who does it in half the amount of time uses more power in order to do that. Okay? So it's the same work, but different power is exerted. The faster the work is done, that's more power. The ability to do work in a certain amount of time. So here's the formula for power. Power is equal work divided by time. P equals W over T. Power equals work divided by time. Okay, power is measured in a unit called watts, W-A-T-T. And there's James Watt, the physicist for which the unit was named. You may recognize that unit probably on light bulbs, right? The number of watts is commonly listed on a light bulb to indicate how much power the bulb uses, and it's usually also equivalent to how much light it gives off. The higher power light bulbs have higher wattages. James Watt invented the steam engine. Okay, and there is his unit. The watt is equal to 1 joule of work performed in 1 second. Okay, again, there's our light bulb, used to measure power of light bulb in small appliances. Your microwave will have a wattage rating. Bigger microwaves might be 1,000, 5,000 watts or something like that, and smaller microwaves, of course, less. And also your electric bill, which you guys don't get yet, but I'm sure your parents or guardians do. And that's going to be also measured in kilowatt hours. So somewhere outside your house, you have a meter spinning around in circles, measuring how many watts of electrical power that you use in your home, and that's how you're billed each month. Okay, a kilowatt, of course, is equal to 1,000 watts. Remember that prefix kilo, like a kilometer, means 1,000. So if you put kilo in front of watt, that is 1,000 watts. A more common power unit, perhaps to some people, is an older unit called a horsepower, which is commonly used for trucks and tractors and machines like that as a rating for how much power they have. Okay, horsepower is actually equal to 750 watts. It was developed to quantify power. A strong horse could move a 750 Newton object 1 meter in 1 second. And that is therefore what a watt is. Okay, so we're going to hold off on the machines part in this PowerPoint. We'll come back to this perhaps later in the week. What I want you guys to do, though, is take a look at this sheet on notability. And we're going to write some notes down on this on work and power. So we discussed what work is. I don't know if you want to do a split screen or notability now, or just watch and go back and forth between the two. But again, we'll discuss. So what is work? Work is when a force is exerted on an object and the object moves in the direction of the force. Okay, so see if I can do a little sketch here. Person applies a force to this box. Okay, and the box slides along the floor a certain distance in this direction. That would be an example of work. Okay, what's the formula for work? Well, we just talked about that. Force, excuse me, erase that while I said force. Work is equal to force times distance. Okay, I don't know if you guys remember our little triangle. We used this with speed equals distance over time and those sorts of formulas, but this helps us to change the formula around to be able to solve for our different variables. So since work equals force times distance, force and distance are on the same base of the triangle there. If we wanted to change the formula around, let's say we want to solve for force. We look on the triangle. I find the F over there for force. I cover that with my finger. And then I see that W is over D on the other side of the triangle. So the formula for force is work divided by distance. Okay, how about if I want to solve for distance? Well, I cover the D for distance up with my finger, and I look, and work is over force. So there's my three variations of that formula that we could possibly use. And when we do problems a little bit later, those will be useful. So again, what are the units for work? Do you guys remember from the PowerPoint? They are joules. Okay, which is, get rid of that, it's sloppy. Abbreviated with a capital J. Okay, same thing for power. What is power? Okay, the definition for power is the rate rate at which work is done. Okay, so again, power is how fast work gets done. If you want to sand your shop project where you're doing some woodworking, you can do the work by hand, where you take a piece of paper and you rub it back and forth, and that's a certain power rating. Then, of course, you can get an electric sander, plug it in, and use it. So, which one's going to allow you to do the job faster? Probably the power sander, and that's because it has a higher power than your hand does to get that work done. Okay, what's the formula for power? Hopefully you remember from the PowerPoint. Power is equal to work over time. So again, if I want to fill in my triangle, power this time is going to go down on the bottom left, W is at the top, and T is at the right bottom corner. Okay, P equals W over T. So what if we want to solve for the other variables in the equation? Well, if I want to solve for work, I cover the W up. Okay, and I look down the bottom, and P and T are on the same level of the triangle, so work is equal to power times time. Or if I want to solve for time, okay, I look on the other side of the triangle, and work is over power. Okay, and what are the units for power? And if you recall our conversation, we talked about the unit known as watts. We also talked about horsepower, but in these power calculations, we're gonna stick with watts. Okay, so that's our discussion for today. We're going to get to this here tomorrow, some of these problems. You might want to just give them a quick look over, but I'm going to have another video where I set you guys up and we do a couple of these, and then that'll be something you need to get done and turned in, but that will be tomorrow's assignment. Okay, I hope everybody's doing well, and check your Schoology every day to see the tasks that you're supposed to complete. They're not going to be terribly long, but hope you're keeping up with it. Send me a message on Schoology if you're having any problems or need any help. Thank you guys. Have a good day.